Welcome to SynCardia, where we manufacture the world's only commercially approved artificial heart. SynCardia is located in Tucson, Arizona, and is comprised of 6 different buildings totaling 34,000 square feet. Roughly half of that is dedicated to operations and manufacturing. We'll start the tour off in SPUZ, where we manufacture the building block of the artificial heart. Then we will go to CES, where we manufacture the heart itself. And then we will end in CASA, where we manufacture and service the drivers that pump the heart. Welcome to the SPUZ lab, where we manufacture SPUZ. SPUZ stands for Segmented Polyurethane Solution and is the building block for all of our artificial hearts. The SPUZ process is a temperature-controlled polymerization process with a unique blend of raw materials, initiators, extenders, and terminators to have a final outcome of a material that meets our mechanical and chemical properties to be used inside of the body. In addition to manufacturing, we also do the final acceptance testing here at SynCardia. At SynCardia, we have a tensile tester to make sure that the SPUZ meets the mechanical properties we need. We also have an FTIR and GPC to make sure that it meets the chemical properties needed as well. SPUZ has about 800 years worth of patient life on it, making it one of the most biocompatible materials out there in the market. This is our reactor for SPUZ, which we utilize to blend all the raw materials to manufacture SPUZ. Think of the reactor as a big KitchenAid. If you are making cookies and you're mixing all your materials together, this is exactly what the reactor does for us. At the end of the process, we repackage all the SPUZ into smaller bottles, which we store in the CES for them to use for manufacturing the heart. Here we are in the CES, and I'll go over the manufacturing process for the artificial heart. So initially, we have to make the ventricle housing for the artificial heart. We do that by utilizing SPUZ, as you can see, which has a high viscosity, similar to honey. And we pour the SPUZ on top of the molds utilizing open cast molding, and then we cure it. So one pour, we'll put it into the oven, we'll cure it, that's one layer. And we'll do this about 18 different times until we get a thickness that meets our specification. As you can see, we've got an embedded mesh in between the layers. So between layers 9 and 10, we'll put a mesh that acts and to give it mechanical strength and to give it the heart a little more robustness during the pumping process. Next part of the process, we're going to add a blood diaphragm. And the blood diaphragm is the one that interacts with the blood and pushes it and also receives the blood in through the heart. The way that we manufacture this is that we utilize a mold where we put the housing on top of it, and we'll pour the SPUZ inside of the mold, and then we'll let it cure upside down. As you can imagine, the shape is concave, so you have a kind of a rounded edge where the spuds will sit, and then it will cure to the outside wall or the inside wall of the heart. Next step, we've got the blood diaphragm assembly. We don't just have one layer for the diaphragm, we've got 4 complete layers. The diaphragm assembly has got 3 layers itself with graphite in between them to act as a lubricating layer. The technicians will take the ventricle with the blood diaphragm layer. They will insert the diaphragm assembly. They'll utilize spuds to glue it to the inside, so you've got 4 complete layers. Next part of the process, you'll have the base cannula assembly. In the base cannula assembly, it seats to the bottom of the ventricle housing to have a complete airtight seal, allowing the air to pressurize and push the diaphragm assembly so that you can pump blood out. And also you have a vacuum cycle where you can pull blood inside to the heart so you can fill and you can pump. Next part of the process is actually a completed TH assembly where you've got 2 different ventricles. To fully complete it, you do have heart valves that you will seat inside of the device itself. The heart valves act as a stop gate to allow blood not to come in at a certain period and then allow blood to come in and fill the heart. The last part of the process that I want to show is the interaction with how the heart works. So as I talked about, you have a pressurization cycle and then you've got a vacuum cycle. Pressurization cycle, you will pump air into the cannula until it pressurizes until it can overcome the systemic pressure. At that point, you will get movement of the diaphragm and an opening of the outflow valve. Blood will expel outside of the heart. Once the valve or the diaphragm is fully distended, the driver will pull a vacuum cycle. So it'll depressurize the cannula, allowing the diaphragm to retrace back to its original position until the system pressure on the inlet side overcomes the valve and allows blood to come in and fill the heart. Repeat the cycle again with pumping. And this occurs on average about 2 times per second for 120 beats per minute. And that is the manufacturing of the artificial heart. Now we are in the failure investigation cell within the CASA building, where we receive drivers that have potentially failed in the field, as well as drivers that have failed in manufacturing, where we investigate, try to find the root cause, and determine a solution to move forward. As being a Class 3 medical device under the FDA, we have the responsibility to report on any failures that we see in the field and any solutions that we need to move forward to make sure that the product is safe for patients. Here we are in the Companion 2 cell in the CASA building. CASA stands for Console Assembly and Service Area, and it's where we service all incoming drivers and manufacture new drivers. As the driver is out in the field and it's reached its certain service cycle, it'll come to SynCardia to be serviced just as you would with your car at a 15,000 mile service cycle, 30,000 service cycle, we also have service cycles here for our drivers. The Companion 2 has a 90-day service cycle. After 90 days of use, it'll come back to be serviced and have components replaced. It's also got a 2-year service cycle where it is calendar days, whether it's been used or not. If it sits on the shelf, it comes back to have components replaced in the driver to ensure that it's safe for patient use. The Companion 2 replaced the console CSS Big Blue device, which used to be 400 pounds and looked like a washing machine, now down to a small form factor, which is more portable. The Companion 2 is the hospital driver, which allows the surgeons and the clinicians to have more control and also have more visuals and diagnostics to see how the patient's doing. If the patient is not clinically stable, they will not be discharged to freedom and they will remain on the C2 device. Here we are in the Freedom cell in the CASA building. The Freedom is the portable driver that the patients are discharged with once they leave the hospital. Once a patient is clinically stable, they will be discharged and they can utilize the Freedom driver either in a backpack, a shoulder bag, or a handbag that they utilize to carry with them. Each patient is sent home with 2 drivers, one being their primary and one being their backup. If anything were to happen to their primary, the patient would switch to their secondary, or their caregiver would switch to their secondary. They would then go to the hospital to receive a replacement backup, so they always have 2 on hand. Here we are in the accessory cell where we service carts, caddies, and retest batteries before they go out into the field. Both the cart and the caddy allow the C2 to be mobile within the hospital. The cart is utilized in the surgical suite to allow for movement of the C2 within that environment, and the caddy is used if the patient needs to be moved for testing, for labs, throughout the hospital, so that the C2 is mobile throughout that process. Here we are in the SynCardia showroom, which is a bonus for the virtual tour. The main thing I wanted to point out was the difference between the Big Blue, which was our historical driver, versus the C2, which is our current existing hospital driver. For the Big Blue, as you can see, it's a larger device, but it was utilized during our first implant in 1985. It was all analog control, as you can see, and also a larger device, about the size of a washing machine. For the C2, it is a smaller device, but also gives you digital readouts and allows you to have a little bit more flexibility with the control. Here we are at the end of our tour. I hope you enjoyed it. I hope it was informative. I want to thank you all for watching, and good luck in the Heart Hackathon.